My name is Dr. Ken Gallardi. Thanks for watching the video on the complete photon model that explains both the particle and wave nature of radiation. If you subscribe, you'll be alerted to when I post other explanations of polarization effects, momentum effects, along with other videos. Now I want to show you how this complete model simply and elegantly describes a way in which all the features of the double slit experiment can be explained. And I emphasize that the credibility of the model is to be determined by the reasonableness of how these explanations flow from the model. And the reasonableness is in the hands of the physics community. The features of the model that are vital and sufficient to explain the double slit experiment are: 1. Quantization of a three-dimensional photon, its probability mechanics, the shell structure, the ability of the shells to separate and unite, and you will see how these features, one is able to explain all of the effects of the experiment when conducted on a photon-by-photon basis. I've sketched a setup of the photon arriving from the left, and at the right of the diagram you'll see the intensity pattern after a large number of photons has reached the screen. It's in the Fraunhofer region. I've also drawn a dashed line to indicate the Fresnel zone. You'll see the diagram is not to scale. Let's look at the Fraunhofer region first. There I've identified where the first 4 photons may have arrived. You'll notice that they each appear as a dot. There's no observable pattern to where they arrive, and if the experiment were done a second time, these 4 points would be different. However, after a large number of photons have arrived, the pattern shown is obtained, and that pattern is the same each time the experiment is performed. This model explains these observations by 1. The photon appears as a dot because of quantization of a three-dimensional photon, which means that any measurement implies that you have absorbed the whole photon, as explained in the previous video. 2. The photons arrive in what seems like a random order, and this is a consequence of the probability mechanics. The direction of a photon travels in it is dictated by the probability signature of the double slit, and at this stage, that distribution is not obvious. 3. After a large number of photons have arrived, a reproducible pattern emerges, and this is characteristic of the probability nature of the direction of travel. A large number of events yields a distribution pattern. So the results in the Fraunhofer region are explained by 2 features of the model, namely that quantization applied to a three-dimensional photon and the probability mechanics of a photon interaction. Now let's move to the Fresnel zone. Observationally, you can't trace the path through this zone, and no pattern is observed even after a large number of photons have gone through the slits. You can only observe photons, but their location does not match the patterns seen in the Fraunhofer region. This model explains these results by recognizing that the double slit perturbation causes the photon to split into shells which travel separately before reuniting. The Fresnel zone is the region in which the photons reunite, and the reunion is dictated by the stability condition, which demands that the shells come together in phase. So, 1, you can't trace the path because the photon shells are not observable. And 2, you can't observe a pattern because an observation, which is a perturbation, in this region induces the photons to come together, otherwise you wouldn't detect it, which destroys the probability pattern the photon left the slits with. So the results in the Fresnel zone are explained by 3 features of the model, namely the probability mechanics and the shell structure, which allows the photons to split into shells that travel separately, and a measurement in the region where the photon shells are separate may observe the photon, but this implies that the perturbation of the measurement has caused the shells to reunite. I suggest that the clear matching of the outcome with the model predictions adds to the confidence one has in the model, and in particular that the mechanics of the photon are probability-based, and the shell structure, including the ability of the shells to separate and unite, is valid. 2 more comments just for clarity. The Fresnel zone is not limited to those photons which are still traveling in their separated shell format, as one is unable to detect when a photon reunites, only that it has reunited or is induced to reunite by the measuring process. one cannot detect the difference between the photon that has been induced to come together and one that has come together naturally, even though there is this technical difference. The edge of the Fresnel zone simply marks out the region in which most of the photons will have regained their stable configuration. Second comment. Mathematically, one is left to use pattern recognition to describe the signature probability associated with the double slit experiment. Well, that's how this model explains the double slit. And I suggest that the clarity of the explanation and the ease with which the model accommodates all the data and the explanation of what is happening in the Fresnel zone should give good credibility to the model. In my next video, I'll be showing how this model explains polarization effects, including when a single photon travels along the optic axis of a birefringent media. Again, the explanation will be simple, elegant, and clear, giving greater credibility to this model of a complete photon. A subsequent video will deal with momentum issues and will show that this photon does not possess a conserved linear momentum. However, it does have a conserved angular momentum, and I'll describe how the model treats spin angular momentum. Well, thanks for watching. Please subscribe to the channel, please add your comments below, and please pass it on to others, particularly those in the physics community. Again, thanks for watching, thanks for your help, and God bless.